In the Oort cloud, where darkness stretches for light years and temperatures hover just above absolute zero, ancient ice drifts through time measured not in years but in geological epochs. Here, suspended in the gravitational embrace of our distant sun, Comet 3I Atlas begins its story, though begins implies a starting point that does not exist in this realm of deep time. The nucleus, no larger than a small mountain yet containing the compressed history of stellar formation, holds water ice, carbon dioxide, methane, and ammonia that have remained chemically unchanged since the solar nebula first collapsed under its own weight 4.6 billion years ago. The Oort cloud itself extends roughly 100,000 astronomical units from the Sun, a distance so vast that light from our star takes over a year and a half to reach these frozen wanderers. Within this spherical shell of primordial debris, gravitational perturbations occur with the patience of continental drift. A passing red dwarf star, dim and invisible to human eyes across dozens of light years, exerts its influence across centuries and millennia, gradually nudging objects from their stable orbits into new trajectories that will carry them sunward on journeys lasting millions of years. Scientists estimate the Oort cloud contains between 1 and 100 trillion of these icy nuclei, yet the space between them remains so immense that collisions occur perhaps once every billion years, less frequently than mass extinction events on Earth. Each nucleus represents a pristine sample of the early solar system's composition, a cosmic core sample locked in a deep freeze that has preserved molecular structures from before Earth's oceans formed, before the Moon's violent birth, before the late heavy bombardments scarred the inner planets with crater chains still visible today. The irony rests in this abundance of information, countless libraries of cosmic history drifting in silence, most destined never to be read by curious minds. Only the rarest gravitational circumstances will ever deliver these archives to the inner solar system, where human instruments can decode their ancient chemistry. For every comet that makes this journey, millions more will orbit in darkness until the sun itself expands into a red giant and boils away their icy cores. 3 Atlas responds to gravitational whispers with the same inevitability that water follows riverbeds toward the sea. Its orbit shifts by microscopic amounts each year, like a planetary clock marking time in millennia rather than seconds. The nucleus rotates slowly, perhaps once every few days, presenting different faces to the weak stellar radiation that bathes its sunlight so attenuated by distance that it provides less illumination than starlight on a clear Earth night. The surface temperature remains constant at approximately negative 270 degrees Celsius, warm enough to allow extremely slow sublimation of the most volatile compounds, but cold enough to preserve the bulk composition intact. Only the most sensitive infrared instruments could detect the faint thermal glow the nucleus emits heat, produced by radioactive decay within its rocky and metallic components, elements forged in stellar cores that died before our sun was born. Crystalline structures within the ice-form patterns that record the temperature and pressure conditions present during the comet's original accretion. These lattices preserve information about the solar nebula's chemistry with the same precision that tree rings record annual climate variations. The nucleus contains noble gases in ratios that reflect the isotopic composition of interstellar space. Xenon and argon atoms that witness the deaths of massive stars and the birth of planetary systems across the galaxy. The mystery lies not in the comet's existence, but in the precise combination of celestial mechanics that selected this particular nucleus for its journey inward. Among trillions of possibilities distributed across light years of space, what specific gravitational choreography chose 3I Atlas to carry its ancient message toward the inner solar system, where human civilization could intercept and decode it? The dynamics that govern such selections remain only partially understood, like trying to predict which individual snowflake will be the first to fall in a coming storm. Computer simulation suggests that roughly 1 comet per year receives the gravitational nudge necessary to begin the million-year journey from the Oort cloud to the inner planets. Most will develop spectacular tails and dissolve under solar heating. their ancient materials dispersing into the interplanetary medium like letters from the past finally opened and read. Others will swing past the sun and return to the outer darkness, their surfaces slightly altered by the brief encounter with stellar radiation. 3i Atlas carries within its frozen matrix amino acids, complex organic molecules, and isotopic signatures that formed in the molecular clouds between stars before our solar system existed. These compounds represent chemical evolution on cosmic scales, reactions that occurred in the vacuum of space at temperatures approaching absolute zero. The nucleus contains more water than all of Earth's rivers combined, locked in crystalline ice that has never known the touch of liquid state. As the comet drifts through its appointed orbit, it remains unaware of its cosmic significance, a messenger from the deep past carrying information about stellar nuclear synthesis, planetary formation, and the chemical foundations of life itself. The irony of this unconscious archive drifting through space while conscious beings on a distant rocky planet develop the technology to read its contents spans billions of years of cosmic evolution. Only took the universe 13 billion years to create observers capable of understanding their own origins through the study of wandering ice. Beyond Neptune's orbit, where the sun appears as nothing more than the brightest star in a field of distant lights, solar winds begin their gentle work on ancient surfaces. The solar wind itself streams outward at speeds approaching 400 kilometers per second, carrying charged particles that originated in nuclear fusion reactions at the sun's core. These particles, primarily protons and electrons, have traveled for 8 minutes from the solar surface to reach Earth's orbit, but require months to reach the realm where 3i Atlas begins its slow acceleration toward the inner system. The comet nucleus, still frozen in its primordial state, starts to feel the first whispers of stellar radiation pressure. At this distance, roughly 40 astronomical units from the sun, solar energy delivers less than 1,000th of the heat that Earth receives. Yet this infinitesimal warming begins the slow transformation that will define the comet's visible existence. The most volatile compounds, carbon monoxide and nitrogen, start to sublimate from the nuclear surface at temperatures still hundreds of degrees below freezing. This initial outgassing occurs so gradually that human observers would need sensitive spectroscopic equipment to detect any change in the comet's appearance. The sublimating gases escape the nucleus at velocities measured in meters per second, slow enough that a walking person could keep pace with the expanding vapor cloud. These gas molecules, liberated from ice matrices that have confined them for billions of years, begin their own independent orbits around the sun while gradually dispersing into the vacuum of interplanetary space. The irony of this awakening lies in its gentleness after eons of absolute stillness. The comet's transformation begins with changes so subtle they would appear motionless to human perception. The nucleus loses perhaps a few kilograms of material per day, a rate so slow that the comet could maintain this level of activity for millions of years without significant alteration to its bulk composition. Only the most patient instruments can measure this cosmic exhale that marks the beginning of the end of the nucleus's pristine state. Solar wind particles strike the expanding gas cloud and create the first faint traces of what will eventually become the comet's distinctive coma. These interactions occur through charge exchange processes, where solar wind protons steal electrons from neutral gas molecules, creating brief flashes of ultraviolet radiation invisible to human eyes but detectable by space-based observatories. The newborn coma extends perhaps a few hundred kilometers from the nucleus, smaller than most major metropolitan areas on Earth. Within this tenuous atmosphere, complex chemical reactions begin to occur for the first time since the comet's formation. Water molecules photodissociate under ultraviolet radiation, breaking apart into hydrogen and hydroxyl radicals that glow with characteristic spectral signatures. Carbon monoxide molecules undergo similar transformations, creating carbon atoms that absorb and re-emit sunlight at specific wavelengths that reveal the comet's chemical composition to distant observers. The nucleus itself remains largely unchanged. its surface temperature still locked at temperatures that would instantly freeze any liquid water. Yet beneath this frozen exterior, the gradual warming begins to create thermal gradients that will eventually drive more dramatic outgassing events. Heat conducts through the nucleus interior at speeds measured in centimeters per year, like warmth slowly penetrating a massive block of ice left outside during a gentle spring thaw. Astronomers detect these early stages of cometary awakening through shifts in the object's brightness and spectral characteristics. The comet appears slightly larger in telescopic observations, though this apparent size increased results from the expanding gas cloud rather than any change to the solid nucleus. Photometric measurements reveal subtle variations in reflected sunlight as different surface regions experience varying degrees of solar illumination during the nucleus's slow rotation. The mystery of this early transformation lies in the precise timing and location of initial outgassing events. Computer models predict general patterns of cometary awakening, but cannot forecast exactly when and where the first jets of sublimating gas will emerge from the nucleus surface. These initial active regions often form along fractures or areas of different surface composition, creating asymmetric patterns of outgassing that will eventually sculpt the comet's tail into complex, flowing structures. The expanding coma begins to interact with the local magnetic field carried by the solar wind, creating the first hints of the comet's eventual tail formation. Charged particles within the gas cloud respond to magnetic forces, starting to stream away from the nucleus in directions determined by the interplanetary magnetic field's orientation. This process occurs so gradually that the comet's tail remains invisible even to powerful telescopes, existing only as statistical variations in particle detector readings aboard distant spacecraft. Gas molecules escaping from the nucleus carry with them microscopic dust grains that have remained embedded in the ice matrix since the comet's formation. These tiny particles, smaller than pollen grains, reflect sunlight and begin to create the faint glow that will eventually make the comet visible to ground-based observers. Each grain represents a sample of the primordial solar nebula, containing silicate minerals and organic compounds that predate the formation of the terrestrial planets. The liberation of this ancient dust occurs through a process of gentle mechanical weathering, as sublimating gas molecules drag solid particles away from the nucleus surface. The escaping dust grains follow ballistic trajectories determined by their size, composition, and the velocity of the gas flow that carries them. Larger particles tend to fall back to the nucleus surface, while smaller grains escape into space to form the beginnings of the comet's dust tail. This early phase of cometary evolution demonstrates the delicate balance between gravitational retention and solar heating that governs the lifetime of these ancient objects. The nucleus remains massive enough to hold on to most of its volatile components, yet thermal energy slowly erodes this primordial archive grain by grain, molecule by molecule. The process resembles a cosmic hourglass, where the sand consists of billion-year-old ice and dust streaming away into the emptiness between worlds. Only took 46 centuries of human astronomy to develop instruments sensitive enough to detect these subtle transformations occurring in the outer reaches of the solar system. In the gravitational realm, where Jupiter reigns as the solar system's most massive planet, celestial mechanics unfold with the precision of clockwork spanning geological ages. The giant planet's influence extends far beyond its visible disk and ring system, reaching across hundreds of millions of kilometers to subtly redirect the trajectories of distant comets, like an invisible shepherd guiding wandering flocks. Jupiter contains more mass than all other planets combined, creating gravitational effects that can accelerate incoming comets to tremendous velocities or fling them back toward the outer darkness from which they came. 3I Atlas approaches this gravitational crossroads with the inevitability of a river flowing toward the sea. The comet's trajectory, calculated by orbital mechanics specialists using centuries of mathematical refinement, curves through space along paths determined by Newton's inverse square law and Einstein's subtle corrections for relativistic effects. At distances measured in astronomical units, Jupiter's gravity exerts forces so gentle that the comet's path bends by mere degrees per year, yet these small deflections accumulate into dramatic changes in the object's ultimate destination. The planet's 4 largest moons, Io, Europa, Ganymede, and Callisto, add their own gravitational signatures to this cosmic dance, creating perturbations within perturbations that require supercomputer calculations to predict accurately. Each moon contributes its mass to the collective gravitational field that shapes incoming trajectories, though their individual effects remain thousands of times weaker than Jupiter's primary influence. The irony lies in how these relatively tiny bodies, smaller than Earth's moon, can still alter the paths of objects that have travelled for millions of years from the Oort cloud. As 3I Atlas passes through Jupiter's gravitational sphere of influence, the comet experiences tidal forces that stretch and compress its nucleus in ways undetectable to human observation, yet significant on molecular scales. The differential gravitational pull between the comet's near and far sides creates internal stresses that may contribute to fracture formation within the ice matrix. These tidal effects remain billions of times weaker than those that Jupiter exerts on its own moons, yet they represent the first external forces to act upon the nucleus since its formation in the primordial solar nebula. Jupiter's magnetosphere, the largest structure in the solar system after the Sun itself, extends its influence across distances greater than the orbit of Saturn. This magnetic bubble, generated by convection currents in the planet's metallic hydrogen core, deflects charged particles and creates radiation environments intense enough to damage spacecraft electronics. The comet's expanding coma begins to interact with this magnetic field, causing subtle changes in the plasma environment that sensitive instruments can detect as variations in radio wave propagation. The planet's atmospheric composition, predominantly hydrogen and helium with traces of methane, ammonia, and water vapor, provides a stark contrast to the complex chemistry emerging from the comet's nucleus, while Jupiter represents the preserved remnants of the solar nebula's original composition. 3I Atlas carries materials that underwent processing in interstellar molecular clouds before the solar system's formation. These two objects, giant planet and tiny comet, represent different chapters in the cosmic story of matter's evolution, from stellar nucleosynthesis to planetary formation. Spacecraft observations reveal that Jupiter's gravity acts as a cosmic filter, determining which long-period comets will become visible to Earth-based observers and which will be ejected from the solar system entirely. Computer simulations suggest that roughly half of all Oort cloud objects that venture into the inner solar system receive gravitational kicks from Jupiter, strong enough to send them on hyperbolic trajectories toward interstellar space. The other half experience more gentle deflections that transform their orbits into elliptical paths, with periods ranging from decades to millennia. The precision required to calculate these gravitational interactions spans multiple scales of space and time. Engineers must account for Jupiter's orbital motion around the Sun, the planet's complex internal mass distribution, and the three-dimensional geometry of the approaching comet's trajectory. Small errors in initial position measurements can propagate into large uncertainties in predicted outcomes, demonstrating the chaotic nature of gravitational dynamics in multi-body systems. This gravitational encounter occurs in almost perfect silence, with no dramatic collisions or visible fireworks to mark the moment when Jupiter's influence fundamentally alters the comet's destiny. The deflection proceeds as smoothly as the rotation of planets themselves, following mathematical laws that govern motion from the scale of subatomic particles to the expansion of the universe itself. Only sensitive measurements of position and velocity can detect the changes occurring. As 3I Atlas passes through this invisible intersection of gravitational forces, the mystery lies in the quantum mechanical foundations that ultimately govern these classical gravitational interactions. While Newton's laws predict the comet's macroscopic trajectory with extraordinary accuracy, the underlying physical processes remain rooted in quantum field theory and general relativity. The curvature of space-time around Jupiter's mass creates the gravitational effects that redirect the comet, Yet this curvature itself emerges from quantum mechanical properties of matter and energy that scientists continue to investigate. Jupiter's role as gravitational shepherd has operated throughout the solar system's history, protecting inner planets from cometary bombardment, while simultaneously directing water-rich objects toward regions where life might eventually emerge. This cosmic balance, neither planned nor random, represents one of many apparent coincidences that made Earth's biological evolution possible. The giant planet's position and mass seem perfectly calibrated to create stable conditions in the inner solar system, though this apparent fine-tuning may simply reflect observational selection effects rather than cosmic design. The comet's passage through Jupiter's gravitational realm marks a transition from the slow, predictable orbital mechanics of the outer solar system to the more complex dynamics that govern objects in the inner planet's domain. From this point forward, 3I Atlas will experience increasingly strong solar heating, more frequent gravitational perturbations from multiple planets, and the gradual disintegration that marks the final chapter of its billion-year journey through space. Only took human civilization 4 centuries to develop the mathematical tools necessary to predict these gravitational encounters with precision exceeding the width of a human hair projected across interplanetary distances. Within the wavelengths of light that span from ultraviolet to infrared, spectroscopic instruments decode the chemical signatures of distant objects with the same precision that archaeologists use to date ancient pottery fragments. The science of spectroscopy reveals that each element and molecule absorbs and emits electromagnetic radiation at characteristic frequencies, creating distinctive fingerprints that persist across billions of kilometers of interplanetary space. When starlight passes through the expanding gas clouds surrounding 3I Atlas, certain wavelengths disappear while others appear enhanced, creating dark absorption lines and bright emission features that tell the story of the comet's composition. Ground-based observatories equipped with high-resolution spectrographs begin detecting unusual chemical signatures in the comet's developing coma that challenge established models of solar system formation. The hydroxyl radical emission lines appear stronger than predicted, suggesting water ice sublimation rates that exceed theoretical calculations based on solar heating alone. Carbon monoxide bands show isotopic ratios that differ subtly from those measured in other comets, indicating formation conditions that may have occurred in different regions of the primordial solar nebula or even in pre-solar molecular clouds. The mystery deepens when astronomers identify spectral features corresponding to complex organic molecules typically associated with interstellar medium rather than solar system objects. Hydrogen cyanide, formaldehyde, and methanol emission lines appear in combinations that suggest chemical processing under conditions of extreme cold and low density characteristic of the space between stars. These molecules should have been destroyed or significantly altered during the comet's formation if it originated entirely within our solar system's gravitational influence. Professional astronomers working at major observatories coordinate their observations to capture spectral data across multiple wavelength ranges simultaneously. The Atacama Large Millimeter Array detects radio emissions from carbon-bearing molecules, while optical telescopes record the visible light scattered by dust grains in the coma. Infrared space telescopes measure thermal emission from the nuclear surface and identify crystalline water ice signatures that reveal the temperature history of the comet's formation environment. The irony emerges in how these sophisticated instruments, representing centuries of technological development, detect chemical processes that occurred before Earth existed. The spectrograph that analyzes light from 3I Atlas contains more computing power than existed in all of human civilization just decades ago. Yet it studies materials that preserve information from an era when the sun itself was merely a collapsing cloud of gas and dust in a stellar nursery that no longer exists. Nitrogen isotope ratios measured in the comet's cyanide emissions suggest formation temperatures below 20 Kelvin, conditions so extreme that molecular motion nearly ceases, and chemical reactions proceed at rates measured in geological timescales. These measurements indicate that significant portions of the comet's volatile inventory formed in the coldest regions of the outer solar nebula or in interstellar space itself, preserving isotopic signatures that predate the solar system's collapse into its current configuration. The detection of deuterium-enriched water vapor adds another layer to this chemical mystery. The ratio of heavy hydrogen to normal hydrogen in the comet's ice appears elevated compared to Earth's oceans, suggesting different formation mechanisms or subsequent processing in environments where deuterium could accumulate preferentially. This isotopic signature provides clues about the temperature and density conditions present during the comet's accretion, information that helps astronomers understand the thermal structure of the early solar system. Spectroscopic observations reveal that the comet's dust component contains crystalline silicate minerals that require high-temperature formation processes, creating an apparent contradiction with the extremely cold conditions indicated by the volatile chemistry. These refractory grains likely formed in the hot inner regions of the solar nebula before being transported outward and incorporated into the icy nucleus during its accretion. The presence of both high-temperature and ultra-low temperature components within the same object demonstrates the complex mixing processes that occurred during planetary formation. Professional spectroscopists employ sophisticated mathematical techniques to extract quantitative information from the observed emission and absorption features. Radiative transfer models account for the effects of optical depth, excitation temperature, and collisional processes within the comet's expanding atmosphere. These calculations require detailed knowledge of molecular physics and quantum mechanics to convert measured light intensities into accurate estimates of chemical abundances and physical conditions. The temporal evolution of spectral features provides additional insights into the comet's internal structure and composition. As solar heating penetrates deeper into the nucleus, different layers release their volatile inventories in sequences that reveal the comet's accretion history. Early observations show predominantly surface materials, while later measurements detect components from progressively deeper regions that have remained unaltered since the object's formation. International collaboration enables round-the-clock spectroscopic monitoring, as Earth's rotation carries different observatories into optimal viewing positions. Radio telescopes in Chile, optical instruments in Hawaii, and infrared satellites in space coordinate their observations to build comprehensive pictures of the comet's chemical evolution. This global effort represents one of astronomy's most sophisticated applications of remote sensing technology to decode the composition of objects too distant for direct sampling. The spectroscopic data accumulated during Triatlas's approach reveals chemical complexity that extends far beyond simple water ice sublimation. Noble gas measurements, when they become detectable, will provide the most direct information about solar system formation conditions, since these chemically inert elements preserve primordial compositions without alteration by subsequent chemical processing. The anticipated detection of helium, neon, and argon isotopes trapped within the comet's structure promises to answer fundamental questions about the solar nebula's evolution and the processes that concentrated materials into the planetesimals that eventually became planets and comets. Only took human science 3 centuries to develop the theoretical framework and instrumental capability necessary to decode chemical messages written in the language of starlight itself. The nucleus of 3I Atlas begins its transformation from a single coherent body into a collection of smaller fragments, each carrying its own portion of the ancient chemical archive that has travelled through deep space for millions of years. This fragmentation process occurs not through violent explosion, but through the gradual weakening of structural bonds as thermal stress creates fractures in the ice matrix, and sublimating gases generate internal pressure that exceeds the nucleus's tensile strength. The comet's gravity, roughly 100,000 times weaker than Earth's, cannot hold the fragments together once mechanical forces overcome the weak cohesion between different compositional layers. High-resolution telescopic observations reveal the emergence of multiple condensations within the comet's expanding coma, each representing a separate nucleus fragment, pursuing its own slightly modified trajectory through the inner solar system. These individual pieces range in size from city blocks to small mountains, maintaining the same basic composition as the original nucleus, while developing distinct patterns of outgassing and dust production. The largest fragments preserve enough mass to continue significant sublimation activity, while smaller pieces lose their volatile inventories more rapidly and fade from telescopic visibility within weeks or months. The fragmentation process follows patterns observed in other disrupted comets, where structural weaknesses created during the original accretion process determine the locations and orientations of eventual breaks. Layered compositions resulting from episodic accretion in the primordial solar nebula create natural fracture planes that separate under thermal stress more readily than the more homogeneous regions between them. The irony lies in how processes that occurred billions of years ago during the comet's formation now dictate the precise manner of its dissolution under the gentle heating of distant sunlight. Each fragment develops its own distinctive coma and dust tail, creating complex visual patterns that challenge observers to track individual components within the expanding debris field. The fragments spread apart at velocities of only a few meters per second, slow enough that human walking pace could keep up with their separation. Yet these small velocity differences accumulate over months into spatial separations measured in thousands of kilometers. Orbital mechanics ensures that each piece follows a slightly different elliptical path around the Sun, with the ensemble gradually dispersing along the original trajectory like a cosmic string of pearls. Spectroscopic analysis of individual fragments reveals compositional differences that provide insights into the internal structure of the original nucleus before fragmentation began. Some pieces show enhanced concentrations of carbon-bearing molecules, while others exhibit stronger water vapor emissions or elevated dust production rates. These variations indicate that the nucleus contained distinct compositional zones, possibly reflecting different formation episodes or varying degrees of thermal processing during its billion-year residence in the Oort cloud. The mystery of cometary fragmentation lies in the precise triggering mechanisms that determine when and how these ancient objects finally succumb to forces that have been acting upon them for millions of years during their approach to the Sun. Computer models can predict general fragmentation patterns based on thermal stress and internal pressure calculations, but cannot forecast the exact timing or geometry of breakup events. The transition from structural integrity to complete dissolution appears to involve complex feedback processes between sublimation rates, internal temperature gradients, and mechanical stress concentrations that remain only partially understood. Photometric measurements track the brightness evolution of each fragment as it develops its own characteristic pattern of volatile loss and dust production. Some pieces exhibit periodic brightness variations that reveal rotation periods ranging from hours to days, while others show more irregular light curves indicating complex tumbling motions or asymmetric mass loss. These observations provide the only direct evidence for the physical properties and internal structure of materials that formed during the earliest phases of solar system evolution. The gravitational interactions between fragments become increasingly negligible as their separation distances grow, yet subtle perturbations from solar radiation pressure and planetary gravity continue to modify their individual trajectories. The largest pieces experience less deflection from radiation pressure due to their higher mass-to-surface area ratios, while smaller fragments respond more dramatically to the gentle push of reflected and absorbed sunlight. This differential effect gradually spreads the fragment ensemble across wider regions of space, creating the potential for future meteor shower events when Earth's orbit intersects the debris stream. Ground-based observers document the fragmentation process through time-lapse photography that reveals the gradual separation and evolution of individual components within the comet's expanding structure. Long exposure images show the development of multiple tails corresponding to different fragments, each oriented according to the local solar wind conditions and radiation pressure environment at the time of observation. These visual records capture one of nature's most gentle destruction processes, where ancient ice slowly returns to its constituent molecules under the influence of stellar radiation. The chemical evolution of individual fragments proceeds independently once they separate, with each piece releasing its volatile inventory at rates determined by its size, composition, and surface area exposed to solar heating. Smaller fragments exhaust their sublimable materials more quickly and transition from active comets to inert rocky bodies within months, while larger pieces may continue outgassing for years or decades. This differential evolution creates a temporal sequence where observers can study different stages of cometary processing simultaneously by examining fragments of various sizes. Professional astronomers coordinate observations across multiple wavelengths to track the chemical and physical evolution of the fragment ensemble as it approaches perihelion. Radio telescopes monitor molecular emission lines from each major piece, while infrared instruments measure thermal emission that reveals surface temperatures and dust production rates. Ultraviolet spectrographs detect the dissociation products created when solar radiation breaks apart the complex molecules sublimating from the nucleus surfaces. The fragmentation of Three-Night Atlas demonstrates the ephemeral nature of these ancient archives, showing how billion-year preservation in the outer solar system gives way to rapid dissolution once thermal equilibrium shifts toward higher temperatures. Each fragment represents a chapter from the same primordial story. Yet their individual evolution paths create opportunities to study different aspects of early solar system chemistry and physics through comparative analysis of their distinct properties and behaviors. Only took the universe 4.5 billion years to create conditions where conscious observers could witness the gentle dissolution of materials that predate the formation of their own planet. The debris field trailing behind the fragmenting nucleus of 3I Atlas creates a three-dimensional map of chemical processes that occurred in the solar nebula before the planets existed, each microscopic grain carrying isotopic signatures that record temperature, pressure, and composition conditions from the earliest phases of solar system formation. This expanding cloud of dust and ice particles follows trajectories determined by the same gravitational and radiation pressure forces that govern planetary motion, yet operates on scales where individual grains behave like tiny spacecraft, pursuing independent orbits around the Sun while gradually dispersing into the vast emptiness of interplanetary space. Sophisticated mass spectrometry techniques, when applied to collected samples or remote spectroscopic observations, reveal isotope ratios that serve as cosmic chronometers, recording the nuclear processes that created these materials in stellar interiors billions of years before the Sun's birth. Oxygen isotopes show variations that indicate formation in different stellar environments, some grains preserving the signatures of massive stars that exploded as supernovae, while others originated in the gentler stellar winds of red giant stars approaching the ends of their nuclear burning phases. The carbon isotope ratios measured in organic compounds within the dust particles tell stories of chemical evolution in the coldest regions of interstellar molecular clouds, where temperatures approach absolute zero and chemical reactions proceed through quantum mechanical tunneling effects, rather than classical thermal activation. These processes created complex organic molecules over timescales measured in millions of years, slowly building the chemical inventory that would eventually become incorporated into planets and, ultimately, biological systems. Laboratory analysis of similar materials from other comets reveals the presence of pre-solar grains, tiny crystalline structures that formed around dying stars and survived the violent collapse and subsequent evolution of the solar nebula. These microscopic time capsules, smaller than bacteria yet older than the solar system itself, preserve direct samples of stellar nucleosynthesis from the galactic environment that existed before our Sun formed. The irony rests in how these infinitesimal particles, invisible without electron microscopy, contain more direct information about cosmic chemical evolution than entire libraries of theoretical astrophysics. The dust trail extends millions of kilometers behind the comet's fragmented nucleus, creating a temporary structure in the solar system that will persist for decades or centuries before dispersing completely into the interplanetary medium. Solar radiation pressure acts differentially on particles of different sizes and compositions, with smaller grains experiencing stronger acceleration away from the Sun, while larger particles follow trajectories more closely tied to the original nucleus's orbital path. This size-dependent segregation creates complex patterns within the dust trail that encode information about the fragmentation process and the internal structure of the original comet. Numerical simulations of dust dynamics require sophisticated computer models that account for the effects of solar gravity, radiation pressure, electromagnetic forces, and gravitational perturbations from all major planets simultaneously. These calculations demonstrate that dust grains released from the comet will eventually spread throughout the inner solar system, with some particles potentially reaching Earth's atmosphere as meteors years or decades after their liberation from the nucleus. The anticipated meteor shower, if detectable, will provide direct samples of primordial solar system materials that can be collected and analysed in terrestrial laboratories. The chemical composition of individual dust grains varies significantly depending on their location within the original nucleus and the temperature conditions they experience during sublimation and release. Some particles consist primarily of silicate minerals formed at high temperatures in the inner solar nebula, while others contain organic compounds and water ice that condensed in the coldest outer regions. This compositional diversity within a single comet demonstrates the complex mixing processes that occurred during the gravitational collapse and evolution of the primordial solar system. Spectroscopic observations of the scattered sunlight reflected by dust particles reveal crystalline structures that preserve information about the thermal history experienced during their formation and subsequent evolution. The degree of crystallinity in silicate grains indicates the maximum temperatures reached during their processing, while the presence of specific mineral phases provides constraints on the pressure and chemical environment present during their crystallization. These measurements offer direct insights into conditions within the solar nebula that cannot be obtained through theoretical modeling alone. The electromagnetic properties of dust grains affect their interaction with solar wind particles and interplanetary magnetic fields, creating complex plasma physics phenomena as the charged dust trail moves through the heliosphere. Some grains acquire electric charges through photoelectric emission and secondary electron impact, causing them to respond to magnetic forces in addition to gravitational and radiation pressure effects. These electromagnetic interactions contribute to the gradual dispersal of the dust trail and influence the long-term evolution of its spatial distribution. Professional astronomers employ polarimetry techniques to study the optical properties of dust grains within the trail, measuring how the polarization of scattered sunlight changes with wavelength and scattering angle to infer information about particle size, shape, and composition. These observations require extremely sensitive instrumentation, capable of detecting polarization changes as small as 1 part in 10,000, pushing the limits of current observational capabilities while providing unique constraints on the physical properties of primordial solar system materials. The temporal evolution of the dust trail creates opportunities to study the same materials under different physical conditions as they move through varying regions of the heliosphere. Grains experience different radiation environments, plasma densities, and magnetic field strengths depending on their position relative to the Sun and major planets, providing natural experiments in space physics that complement laboratory studies of similar materials under controlled conditions. International space agencies coordinate spacecraft observations and ground-based measurements to create comprehensive maps of the dust trail's three-dimensional structure and chemical composition. These coordinated campaigns represent some of the most sophisticated remote sensing efforts ever applied to study solar system formation processes, combining data from multiple satellites, ground-based telescopes, and theoretical models to reconstruct the detailed history of materials that witnessed the birth of worlds. The gradual dispersal of 3I Atlas's dust trail marks the final transformation of concentrated primordial materials back into the diffuse interplanetary medium from which they originally condensed billions of years ago, completing a cosmic cycle that spans the entire history of the solar system, while providing temporary opportunities for scientific investigation of processes that shaped planetary formation. only took human technology 5 decades to develop instruments sensitive enough to decode chemical messages preserved in dust grains smaller than the period at the end of this sentence. The trajectory of 3I Atlas follows a hyperbolic path through the solar system, a mathematical curve that distinguishes it from the elliptical orbits of planets and most other comets by indicating an origin beyond the Sun's gravitational dominance. Orbital mechanics calculations reveal that this ancient wanderer approaches the inner solar system with an excess velocity that cannot be explained by gravitational acceleration from our Sun alone, suggesting that it carries momentum inherited from its motion through interstellar space, or from gravitational encounters with other stellar systems during its million-year journey toward our cosmic neighborhood. Precise astrometric measurements conducted over months of observation allow astronomers to calculate the comet's orbital eccentricity with extraordinary accuracy, revealing values greater than unity that mathematically define hyperbolic trajectories. These calculations require corrections for relativistic effects, atmospheric refraction, stellar aberration, and the gravitational influences of all major planets to achieve the precision necessary to distinguish between barely elliptical and slightly hyperbolic orbits. The distinction carries profound implications for understanding the comet's ultimate fate and origin. The hyperbolic nature of the orbit indicates that 3I Atlas will complete only a single passage through the inner solar system before escaping permanently to interstellar space, never to return to the Sun's gravitational embrace. This one-time visitor status makes every observation precious, as no future generation of astronomers will have the opportunity to study this particular messenger from the outer darkness. The irony lies in how millions of years of journey culminate in a brief few months of visibility before eternal departure into the cosmic void between stars. Computational analysis of the comet's trajectory, when extrapolated backward through time, suggests possible origins in stellar systems tens or hundreds of light-years distant. The precision required for such calculations exceeds the accuracy of current observational data, creating uncertainties that span vast regions of the galaxy and multiple possible source locations. Some models indicate gravitational ejection from a planetary system around a nearby red dwarf star, while others suggest formation in the outer regions of a more massive stellar system before gravitational perturbations sent it wandering between the stars. The velocity vector of 3I Atlas relative to the local standard of rest provides clues about its motion through the galaxy before entering the solar system's sphere of influence. This measurement requires sophisticated corrections for the Sun's orbital motion around the galactic center, local stellar kinematics, and the gravitational effects of nearby stellar associations. The results suggest that the comet's interstellar velocity remained relatively low, consistent with ejection from a stellar system within the Sun's local galactic neighborhood, rather than arrival from more distant regions of the galaxy. Professional dynamicists employ numerical integration techniques to model the comet's past trajectory through the complex gravitational environment of local stellar space, accounting for the known positions and motions of nearby stars over the past million years. These calculations reveal that 3I Atlas likely experienced multiple close encounters with other stellar systems during its interstellar journey, each encounter potentially altering its trajectory and velocity through gravitational slingshot effects that could have originated anywhere within a sphere hundreds of light-years in radius. The mystery deepens when theoretical models attempt to explain how objects like 3I Atlas acquire the specific combination of velocity and trajectory needed to intersect the solar system's planetary region. Statistical analyses suggest that such encounters should occur rarely, perhaps once per decade or century. Yet the discovery of several interstellar visitors in recent years indicates either remarkable observational coincidence or systematic underestimation of the population of objects traveling between stellar systems. Gravitational dynamic simulations demonstrate that planetary systems naturally eject significant fractions of their primitive materials during the chaotic early phases of planet formation, creating populations of interstellar comets and asteroids that wander the galaxy carrying information about conditions in their birth systems. These ejected objects preserve chemical and physical records of planetary formation processes occurring around different types of stars, potentially providing comparative data about solar system formation that cannot be obtained through study of our own system's remaining members alone. The orbital geometry of 3I Atlas's passage through the solar system offers optimal viewing conditions for Earth-based observers, with the comet's trajectory carrying it through regions of space where solar illumination and viewing angles combine to maximize its apparent brightness and spectroscopic accessibility. This favorable geometry represents a cosmic coincidence that enables detailed study of an interstellar visitor under conditions that may not recur for decades or centuries when the next such object arrives from the space between stars. Advanced spacecraft mission planners evaluate the possibility of rapid deployment of interplanetary probes to intercept 3I Atlas during its solar system passage, though the short notification time and extreme delta-V requirements make such missions extremely challenging with current technology. The scientific value of direct sampling or close-up imaging of a confirmed interstellar object would justify extraordinary engineering efforts. Yet the practical constraints of orbital mechanics and spacecraft capabilities limit options to the most advanced propulsion systems under development. The discovery and characterization of 3I Atlas represents a landmark achievement in observational astronomy's ability to detect and analyze objects that spend most of their existence in the darkness between stars. The techniques developed for tracking and studying this interstellar messenger will enable more systematic searches for similar objects, potentially revealing a previously hidden population of wandering materials that carry information about planetary formation processes occurring throughout the local region of the galaxy. International space agencies coordinate ground-based and space-based observations to maximize the scientific return from this unique opportunity to study pristine materials from another stellar system. The collaborative effort demonstrates humanity's growing capability to investigate cosmic processes on scales that span light years and billions of years, using tools and techniques that barely existed when the first interstellar visitors were predicted by theoretical astrophysics decades ago. The hyperbolic trajectory of 3I Atlas serves as a gravitational signature written in the mathematics of celestial mechanics, encoding information about the comet's billion-year journey through interstellar space in the precise geometry of its path through our solar system. This mathematical record provides the only direct evidence for the object's exotic origin and ultimate destination among the stars. Only took human civilization 4 centuries to develop the mathematical and observational tools necessary to recognize visitors from other stellar systems and decode the stories written in their orbital trajectories. The brightness variations of 3I Atlas follow patterns that reveal the internal architecture of its nucleus, fluctuations in reflected sunlight that encode information about rotational periods, surface composition, heterogeneity, and the three-dimensional structure of an object that has remained essentially unchanged since its formation in the primordial solar nebula billions of years ago. Photometric observations conducted over weeks and months detect periodic variations in luminosity that correspond to the nucleus's rotation. As different surface regions with varying albedo and composition present themselves to solar illumination during the comet's slow tumbling motion through space. The rotation period, measured at approximately 15 hours through careful analysis of brightness oscillations, suggests a nucleus that has experienced minimal collisional modification during its long residence in the Oort cloud or interstellar space. Objects that undergo frequent impacts typically develop more rapid rotation rates, as angular momentum from glancing collisions accumulates over time, while pristine bodies preserve the slow spins acquired during their original accretion from the gravitational collapse of planetesimal swarms in the outer solar nebula. Detailed analysis of the brightness curve reveals asymmetries that indicate significant structural heterogeneity within the nucleus, with some surface regions reflecting substantially more sunlight than others due to variations in ice composition, dust coverage, or crystalline structure. These variations suggest that 3I Atlas formed through the gradual accumulation of materials with different thermal histories and chemical compositions. possibly representing multiple accretion episodes or incorporation of pre-existing objects with distinct evolutionary pathways through the early solar system. The nucleus appears to possess a highly porous structure, with bulk density estimates indicating that up to 70% of its volume consists of empty space between loosely consolidated ice and dust components. This extremely low density, comparable to that of fresh snow or aerogel materials, results from gentle accretion processes that occurred under microgravity conditions in the outer regions of the solar nebula, where collisional velocities remain too low to compact the accreting materials into dense, solid structures. Thermal modelling of the nucleus interior reveals complex temperature gradients that develop as solar heating penetrates through the porous matrix at rates determined by thermal conductivity, sublimation cooling, and the three-dimensional geometry of internal void spaces. Heat conduction proceeds slowly through the low-density structure, creating temperature differences of hundreds of degrees between the illuminated surface and the interior regions that remain at temperatures approaching absolute zero even during close approaches to the Sun. The porosity also affects the mechanical properties of the nucleus, creating a structure that responds to thermal stress and tidal forces in ways that differ dramatically from solid rocky bodies. The loosely bound assembly of ice and dust components can accommodate significant structural deformation without fracturing, yet remains vulnerable to disruption when internal gas pressure from sublimating volatiles exceeds the weak cohesive forces that hold the components together. Spectroscopic observations reveal that different regions of the rotating nucleus exhibit varying degrees of crystalline order in their water ice components, indicating different thermal processing histories or formation conditions. Some surface areas show the spectral signatures of amorphous ice that formed through vapor deposition at extremely low temperatures, while other regions contain crystalline ice phases that require higher formation temperatures or subsequent thermal annealing to develop their ordered molecular structures. The mystery lies in understanding how such a fragile, porous structure could survive billions of years in the harsh radiation environment of interstellar space or the Oort cloud without complete sublimation or structural collapse. Theoretical calculations suggest that objects with such low densities should lose their volatile components much more rapidly than observed. Yet, 3I Atlas clearly retains sufficient ice inventory to support vigorous outgassing activity as it approaches the inner solar system. Computer simulations of porous ice structures reveal complex relationships between porosity, thermal conductivity, and sublimation rates that may explain the enhanced preservation of volatile materials in low-density cometary nuclei. The network of void spaces creates insulating barriers that slow heat conduction while providing pathways for sublimated gases to escape without building up internal pressures that could disrupt the overall structure. This delicate balance between preservation and loss operates over timescales that span the age of the solar system. Professional astronomers employ sophisticated photometric techniques to extract maximum information from brightness measurements, using statistical analysis methods to separate genuine physical variations from instrumental noise and atmospheric effects. These observations require extremely stable instrumentation and careful calibration procedures to detect brightness changes as small as 1% against the varying background of Earth's atmosphere and scattered moonlight. The layered structure implied by the photometric variations suggests that 3I Atlas preserves a stratigraphic record of conditions in the outer solar nebula, with different compositional zones recording the chemical and thermal environment present during different phases of its accretion history. Each layer potentially contains unique isotopic signatures and mineral assemblages that provide snapshots of the evolving protoplanetary disk during the critical period when planets and smaller bodies were forming throughout the system. Advanced image processing techniques applied to high-resolution telescopic observations attempt to resolve the nucleus shape and surface features directly, though the comet's small size and enormous distance make such measurements extremely challenging with ground-based instruments. Space-based telescopes offer better angular resolution, but limited observing opportunities due to pointing constraints and competing scientific priorities for the world's most advanced astronomical facilities. The brightness variations of 3I Atlas also encode information about the optical properties of dust grains in the developing coma, as reflected sunlight from these particles contributes to the overall photometric signal in ways that depend on grain size distribution, composition, and scattering geometry, separating the contributions from nucleus surface reflection, and coma scattering requires sophisticated modelling of radiative transfer processes in the expanding gas and dust environment surrounding the active comet. International collaborations coordinate photometric observations across multiple sites to ensure continuous monitoring coverage as Earth's rotation carries individual observatories in and out of optimal viewing conditions. These campaigns generate datasets spanning months of continuous brightness measurements, with temporal resolution sufficient to detect rotational variations, secular brightening trends, and episodic outgassing events that reveal the complex interplay between solar heating and internal structure in determining the comet's observable properties. Only took human observers 3 centuries to develop photometric techniques sensitive enough to decode structural information about objects billions of kilometers away through careful measurement of tiny brightness variations in reflected starlight from the sublimating surface of 3I Atlas. Jets of gas emerge with velocities measured in hundreds of meters per second, creating temporary atmospheric phenomena that transform the ancient nucleus into a dynamic, evolving system for the first time since its formation in the outer regions of the primordial solar nebula. These gas jets follow the same physical principles that govern volcanic eruptions on terrestrial planets, though operating under conditions of near-perfect vacuum and temperatures that would instantly freeze any liquid water, creating ephemeral structures that exist only as long as solar heating maintains the sublimation processes that drive their formation. The emerging gas streams consist primarily of water vapor, carbon dioxide, carbon monoxide, and trace amounts of more exotic molecules including hydrogen sulfide, ammonia, and complex organic compounds that carry the chemical signatures of interstellar molecular cloud processing. Each jet originates from active regions on the nucleus surface, where solar heating has created conditions favourable for rapid sublimation, typically areas with enhanced exposure to direct sunlight, or regions where subsurface ice lies closer to the surface due to local topographic features or compositional variations. Professional astronomers detect these gas emissions through high-resolution spectroscopy that identifies the characteristic wavelengths emitted when solar ultraviolet radiation excites the sublimated molecules to higher energy states. The intensity and velocity distribution of these spectral lines reveal information about the temperature, density, and expansion velocity of the gas within each jet, providing insights into the physical processes occurring at the nuclear surface and the internal pressure conditions that drive the outgassing phenomena. The 3-dimensional structure of gas jets creates complex patterns within the comet's expanding coma, with individual streams maintaining their identity for distances of thousands of kilometers before turbulent mixing and collisional processes blend them into the more uniform background atmosphere. High-resolution imaging reveals spiral patterns, bow shock structures, and other fluid dynamic phenomena that result from the interaction between directed gas flows and the broader coma environment under conditions that cannot be replicated in terrestrial laboratories. The irony of this atmospheric activity lies in its temporary nature after billions of years of dormancy. The nucleus experiences perhaps its only period of dynamic gas emission during the brief few months of its passage through the inner solar system, before returning to frozen inactivity for the remainder of its existence. These ephemeral atmospheres represent the dying breath of ancient ice, releasing molecules that have remained locked in crystalline matrices since before the formation of the terrestrial planets. Computer simulations of gas-jet dynamics require sophisticated computational fluid dynamics models that account for the transition from subsurface sublimation through surface escape to expansion into the vacuum of space. These calculations must consider the effects of molecular collisions, radiative heating and cooling, chemical reactions between different gas species, and the influence of dust particles that become entrained in the expanding gas flows and modify their thermodynamic properties through momentum and energy exchange. The temporal evolution of gas jet activity follows daily cycles controlled by the nucleus rotation period. As different active regions rotate into and out of direct solar illumination, morning jets develop as sunrise illuminates previously shadowed surface areas, while evening jets fade as active regions rotate into darkness and surface temperatures drop below the sublimation threshold for the dominant volatile species. These diurnal variations provide direct evidence for the relationship between solar heating and cometary activity. Spectroscopic monitoring reveals that different jets exhibit distinct chemical compositions, indicating heterogeneous distribution of volatile materials within the nuclear structure. Some jets show enhanced carbon monoxide emissions suggesting subsurface reservoirs of this highly volatile compound, while others exhibit stronger water vapor signals indicating regions dominated by ordinary ice. These compositional variations preserve information about the chemical gradients that existed in the outer solar nebula during the comet's formation epoch. The interaction between gas jets and the local solar wind environment creates complex plasma physics phenomena as the neutral gas becomes ionized through photoionization and charge exchange processes. The ionized gas responds to magnetic forces carried by the solar wind, creating the beginnings of the comet's characteristic plasma tail that will become more prominent as the object approaches closer to the Sun, and gas production rates increase exponentially with enhanced solar heating. Professional observatories coordinate multi-wavelength campaigns to study gas-jet phenomena across the electromagnetic spectrum, from radio observations of molecular transitions to ultraviolet measurements of atomic emission lines produced when solar radiation dissociates the sublimated molecules. These comprehensive studies reveal the complex relationships between nuclear composition, surface processes, and the development of cometary atmospheres under the influence of stellar radiation. The pressure gradients created by expanding gas jets influence the motion of dust particles liberated from the nuclear surface, creating size-dependent segregation effects as smaller grains become entrained in the gas flow, while larger particles follow more ballistic trajectories determined primarily by the nucleus's weak gravitational field. This differential behavior creates complex dust distribution patterns within the coma that encode information about both the gas dynamics and the size distribution of refractory materials embedded within the sublimating ice. Advanced theoretical models attempt to explain the triggering mechanisms that determine which surface regions become active and develop gas jets under specific illumination conditions. The relationship between local surface composition, thermal properties, subsurface structure, and the threshold conditions required for sustained outgassing activity remains only partially understood, representing one of the outstanding challenges in cometary physics research. The gas jets of 3I Atlas create temporary structures in space that demonstrate fundamental principles of fluid dynamics, thermodynamics, and plasma physics, operating under extreme conditions that extend the boundaries of laboratory experience. These natural experiments in rarefied gas dynamics provide unique opportunities to study physical processes that govern atmospheric escape from planetary bodies throughout the solar system and beyond. International collaborations employ increasingly sophisticated instruments to resolve individual gas jets and measure their physical properties with unprecedented detail, pushing the limits of ground-based and space-based observational capabilities while providing crucial data for testing theoretical models of cometary physics and the fundamental processes that govern volatile loss from small solar system bodies. Only took human science 4 centuries to develop the theoretical understanding and observational techniques necessary to study atmospheric phenomena occurring around objects smaller than cities, yet located millions of kilometers away in the vacuum of interplanetary space. The magnetic environment surrounding 3I Atlas preserves signatures of processes that occurred during the earliest phases of solar system formation, when magnetic fields embedded in the collapsing solar nebula influenced the distribution and transport of materials that would eventually accrete into planets, moons, and smaller bodies like comets. These ancient magnetic records, locked within the crystalline structure of metallic grains and refractory minerals embedded throughout the nucleus, provide direct evidence for the strength and geometry of magnetic fields that existed in the protoplanetary disk billions of years before the current solar system architecture stabilized into its familiar configuration. The solar wind carries its own magnetic field outward from the Sun at velocities approaching 400 kilometers per second, creating a dynamic, magnetized plasma environment that interacts with the expanding gas and dust cloud surrounding the active comet nucleus. When the solar wind encounters the comet's neutral atmosphere, charge exchange processes and photoionization create populations of charged particles that respond to magnetic forces, beginning the formation of the characteristic plasma tail that will become increasingly prominent as gas production rates increase during the approach to perihelion. Spacecraft magnetometers, when available for cometary encounters, detect magnetic field variations that reveal the interaction between solar wind plasma and the comet's expanding atmosphere with temporal resolution measured in fractions of seconds. These measurements show complex magnetic field draping patterns as the interplanetary field lines become distorted by their passage through regions of enhanced plasma density created by ionization of the comet's outgassing materials. Professional plasma physicists employ sophisticated theoretical models to interpret these magnetic signatures and extract information about fundamental processes governing the interaction between stellar winds and planetary atmospheres throughout the universe. The cometary environment provides natural laboratories for studying magnetic reconnection, plasma instabilities, and particle acceleration mechanisms under conditions that cannot be fully reproduced in terrestrial experiments or computer simulations. The nucleus itself likely contains remnant magnetization acquired during its formation in the magnetized solar nebula. Though detecting these weak magnetic signatures requires extremely sensitive instruments and careful separation of the nucleus field from the much stronger interplanetary magnetic field carried by the solar wind, theoretical calculations suggest that the comet's original magnetic record could provide unique constraints on the strength and structure of magnetic fields in the outer regions of the protoplanetary disk, where volatile-rich planetesimals formed. Ancient magnetic fields influenced the transport and concentration of materials during planetary formation by coupling to charged dust grains and ionized gas within the evolving protoplanetary disk. These magnetohydrodynamic processes help determine the radial distribution of different chemical species, potentially explaining the compositional gradients observed between inner rocky planets and outer ice-rich bodies like Thruai Atlas. The magnetic environment also affected the accretion timescales and structural properties of forming planetesimals. The mystery lies in understanding how magnetic information from the early solar system could survive billions of years of storage in the Oort cloud or interstellar space, where cosmic ray bombardment and thermal cycling might be expected to erase or modify the original magnetic signatures. Theoretical studies suggest that certain mineral phases could preserve stable magnetic domains over such extended timescales, but direct observational confirmation requires sophisticated paleomagnetic analysis techniques applied to actual cometary samples. Laboratory studies of meteoritic materials provide analogous examples of magnetic record preservation in primitive solar system objects, revealing that some materials retain magnetic information from magnetic field exposure that occurred during the earliest phases of solar system formation. These terrestrial samples demonstrate the feasibility of magnetic record preservation over billion-year timescales and provide calibration standards for interpreting similar signatures that might be detected in cometary materials. The interaction between the comet's magnetic environment and energetic charged particles creates additional observable phenomena, including radio emissions produced by synchrotron radiation from electrons spiraling around magnetic field lines. These radio signals, though extremely weak, can be detected by large radio telescope arrays and provide complementary information about the magnetic field geometry and particle populations within the comet's expanding atmosphere. Advanced plasma simulation codes model the complex magnetohydrodynamic processes occurring as solar wind plasma encounters the comet's neutral and ionized atmosphere, accounting for the effects of magnetic field line draping, plasma instabilities, and the formation of boundary layers between different plasma regimes. These simulations require massive computational resources to resolve the range of spatial and temporal scales involved in cometary plasma physics. The temporal evolution of magnetic signatures follows patterns related to the comet's changing gas production rate, orbital geometry relative to the solar wind flow direction, and variations in the interplanetary magnetic field strengthen orientation. Solar wind conditions vary dramatically with solar cycle phase, creating different interaction regimes that provide opportunities to study cometary plasma physics under a range of external driving conditions. Professional space physics researchers coordinate observations from multiple spacecraft positioned throughout the solar system to study the propagation of disturbances created by cometary plasma interactions as they travel outward with the solar wind. These studies reveal how local plasma processes around individual comets can influence the broader heliospheric environment and contribute to our understanding of space weather phenomena affecting planetary magnetospheres. International collaborations develop increasingly sophisticated instruments for measuring weak magnetic fields in space environments, pushing the boundaries of magnetometer technology to achieve the sensitivity required for detecting the subtle magnetic signatures associated with cometary processes. These technological advances benefit both fundamental plasma physics research and practical applications in space weather monitoring and planetary exploration. The magnetic record preserved within 3I Atlas represents a unique archive of information about magnetic field processes in the early solar system, potentially providing insights into fundamental questions about planetary formation that cannot be addressed through study of more evolved objects like planets and asteroids that have undergone extensive thermal and chemical processing since their formation. Theoretical astrophysicists employ the magnetic signatures detected in cometary environments to constrain models of protoplanetary disk evolution and magnetic field generation in young stellar systems, extending our understanding of planetary formation processes to other stellar systems, where similar magnetic interactions may govern the assembly of planetary systems around stars throughout the galaxy. Only took human science 5 centuries to develop the theoretical framework and instrumentation necessary to study magnetic field processes occurring in the vacuum of space around objects carrying magnetic records from the birth of the solar system itself. Through the patient accumulation of photons across nights of observation, astronomical photographers capture light that has travelled millions of kilometres from 3I Atlas, each image preserving visual evidence of processes that occurred billions of years ago when the comet's constituent materials first condensed from the cooling vapours of the primordial solar nebula. Long-exposure photographs reveal the asymmetric tail structure that develops as solar radiation pressure and magnetic forces shape the expanding cloud of dust and ionized gas into flowing patterns that extend across angular distances measured in degrees of sky, creating some of the largest visible structures in the solar system. The photographic plates and digital sensors that record these images detect ancient dust grains smaller than the wavelength of visible light, particles that scatter and absorb sunlight according to their size, composition, and crystalline structure. Each grain represents a microscopic sample of the early solar system's inventory of refractory materials, silicate minerals and organic compounds that formed under conditions radically different from those present in the modern interplanetary region. The irony lies in how these infinitesimal particles, individually invisible to human eyes, combine to create the sweeping visual spectacle that makes comets among the most recognizable astronomical phenomena. Professional astrophotographers employ sophisticated imaging techniques that combine multiple exposures taken over hours or days to reveal faint structural details within the comet's tail and coma that remain invisible to visual observation. These composite images show spiral patterns, streamers, and disconnection events that result from the complex interaction between the comet's outgassing activity and the varying conditions in the solar wind environment as the object moves through different regions of interplanetary space. The dust particles responsible for the comet's visual appearance range in size from submicron grains comparable to smoke particles to pebble-sized chunks that follow ballistic trajectories determined by the balance between solar radiation pressure and the nucleus's weak gravitational field. This size distribution creates wavelength-dependent scattering effects that give cometary tails their characteristic colours, with smaller particles scattering blue light more efficiently, while larger grains reflect sunlight more neutrally across the visible spectrum. Theoretical calculations of radiation pressure effects demonstrate that dust grains smaller than approximately 1 micrometer experience accelerations away from the sun that exceed the gravitational attraction, causing these particles to stream away from the comet at velocities that can reach hundreds of meters per second. Larger particles experience weaker radiation pressure and follow more curved trajectories that create the broad, curved dust tail visible in long exposure photographs. The temporal evolution of tail structure provides insights into the history of outgassing activity and internal processes within the fragmenting nucleus over timescales ranging from days to months. Successive photographs reveal the development and dissipation of individual streamers within the tail, each feature corresponding to specific outgassing events that occurred weeks or months earlier when the dust grains were first liberated from the nucleus surface. Professional astronomers employ photometric analysis techniques to measure the brightness distribution along the comet's tail and extract quantitative information about dust production rates, particle size distributions, and the temporal evolution of outgassing activity. These measurements require careful calibration procedures to account for atmospheric extinction, instrumental response variations, and contamination from background stars and galaxies that appear projected against the comet's extended structure. The preservation of prehistoric dust within cometary nuclei demonstrates the remarkable stability of these ancient archives under the extreme conditions of interstellar space, or the outer solar system. Laboratory studies of similar materials suggest that organic compounds and crystalline structures can remain intact for billions of years when shielded from energetic radiation and maintained at temperatures approaching absolute zero. Though the mechanisms responsible for such preservation remain only partially understood, colour photography reveals subtle variations in the spectral properties of different regions within the comet's tail and coma, indicating compositional heterogeneity in the dust population that reflects the complex internal structure of the original nucleus. Some tail regions appear more neutral in colour, suggesting dominance by silicate minerals, while others show enhanced reddening that indicates higher concentrations of organic compounds or iron-bearing materials. Advanced image processing techniques applied to high-resolution photographs attempt to resolve individual dust jets and track their evolution as they expand away from the nucleus and blend into the broader tail structure. These studies reveal the three-dimensional geometry of outgassing processes and provide constraints on models of surface activity and internal structure that cannot be obtained through other observational approaches. The optical properties of cometary dust provide insights into the physical and chemical conditions present during grain formation in the early solar system, as the efficiency of light scattering depends sensitively on particle size, shape, composition, and internal structure. Polarimetric observations complement photographic studies by measuring how the polarization state of scattered light varies with wavelength and scattering angle, providing additional constraints on grain properties. International photographic campaigns coordinate observations from multiple sites around the world to ensure continuous monitoring coverage as Earth's rotation and orbital motion create varying viewing geometries for the comet's tail structure. These collaborative efforts generate comprehensive data sets that reveal both rapid changes occurring over hours and gradual evolution patterns that develop over months of the comet's approach to perihelion. Digital image archives preserve these photographic records for future scientific analysis using techniques that may not yet exist, ensuring that the visual information captured during 3 Atlas's brief passage through the inner solar system remains available for researchers who will develop new methods for extracting information from astronomical images. The photographs themselves become historical documents, recording humanity's first detailed observations of confirmed interstellar materials. The aesthetic beauty of cometary photography often overshadows its scientific significance. Yet these images contain quantitative information about fundamental processes governing the evolution of planetary systems that extends far beyond their visual appeal. Each photograph represents a scientific measurement that contributes to our understanding of cosmic chemical evolution and the distribution of organic materials throughout the galaxy. Professional astronomical societies maintain standardized procedures for archiving and cataloging cometary photographs to ensure their long-term preservation and accessibility to future generations of researchers. These archives represent irreplaceable scientific resources that document rare astronomical events and preserve observational data that cannot be repeated or replicated through laboratory experiments or theoretical calculations. Only took human technology 2 centuries to develop photographic techniques sensitive enough to capture and preserve images of dust grains that contain more information about solar system formation than entire libraries of theoretical astrophysics textbooks. As 3I Atlas approaches its closest point to the Sun, the ancient nucleus experiences temperatures that rise above the sublimation threshold for water ice for the first time in millions of years, marking the transition from the slow, gentle outgassing that has characterized its passage through the outer solar system to the more dramatic volatile loss that will define its final months as a coherent object. Perihelion, the moment of closest solar approach, represents the climactic phase of the comet's billion-year journey from the Oort cloud. When solar heating reaches maximum intensity and transforms the pristine nucleus into a dynamic, rapidly evolving system that releases its ancient chemical inventory at rates thousands of times greater than during its dormant phase, the surface temperature of the nucleus climbs steadily, as the inverse square law of radiation delivers increasingly intense solar heating to the rotating body, creating thermal gradients that penetrate deeper into the porous interior and mobilize volatile compounds that have remained frozen in subsurface reservoirs since the comet's formation in the primordial solar nebula. Computer simulations of thermal diffusion through the low-density nuclear structure indicate that significant warming extends only a few meters below the surface. Yet this shallow heated zone contains sufficient volatile material to sustain vigorous outgassing activity for months or years. Professional astronomers monitor the comet's brightness evolution as it approaches perihelion, documenting exponential increases in luminosity that result from enhanced dust and gas production driven by the rapidly rising surface temperatures. Photometric observations reveal brightness changes of several magnitudes over periods of weeks, indicating volatile loss rates that exceed the comet's ability to replenish surface materials through internal transport processes, leading to the gradual exposure of deeper compositional layers with potentially different chemical signatures. The mystery lies in predicting exactly how individual comets will respond to intense solar heating, as each nucleus possesses unique internal structure, composition, and thermal properties that determine the relationship between solar energy input and observable outgassing activity. Some comets exhibit smooth, predictable brightness increases during perihelion approach, while others display erratic behavior including sudden brightening events, fragmentation episodes, or complete disintegration under thermal stress that exceeds their structural integrity. Water ice sublimation becomes the dominant process governing the comet's activity, as surface temperatures climb above the critical threshold of approximately 200 Kelvin, liberating water vapor at rates that can reach tons per second for large, active nuclei. This water vapor carries with it embedded dust grains and creates the characteristic hydrogen cloud that extends millions of kilometers around the nucleus, as solar ultraviolet radiation dissociates the water molecules into hydrogen and hydroxyl radicals that glow with distinctive spectral signatures. The approach to perihelion also marks the period of maximum scientific opportunity, when enhanced brightness and activity make the comet accessible to the full range of astronomical instruments and observational techniques. Ground-based telescopes can resolve structural details within the coma and tail, Space-based observatories can detect faint spectral features from trace chemical species, and radio telescopes can monitor molecular emission lines that reveal the composition and physical conditions within the expanding atmosphere. Thermal modelling of the nucleus interior reveals complex feedback processes between solar heating, volatile sublimation, and internal heat transport that create nonlinear responses to changing solar energy input. As volatile materials sublimate and escape, they leave behind refractory dust and rock that can form insulating layers on the surface, potentially reducing the efficiency of further heating and creating self-limiting mechanisms that moderate the comet's activity levels. The gravitational environment near perihelion becomes increasingly complex as the comet moves rapidly through regions where solar gravity dominates and tidal forces reach maximum strength. These gravitational effects can contribute to nucleus fragmentation by creating differential forces between different parts of the loosely consolidated structure, particularly when combined with internal gas pressure from rapid volatile sublimation and thermal stress from uneven heating patterns. Professional spectroscopists coordinate intensive observing campaigns during the perihelion passage to capture comprehensive chemical inventories of materials being released from the nucleus interior, potentially including rare molecular species that remain undetectable during lower activity phases. These observations provide unique opportunities to study the most primitive chemical compositions preserved within cometary nuclei, materials that represent direct samples of the outer solar nebula's volatile inventory. The plasma environment around the comet becomes increasingly dynamic as enhanced gas production creates denser ionized atmospheres that interact more strongly with the solar wind, potentially generating observable radio emissions, magnetic field disturbances, and other plasma physics phenomena that provide insights into fundamental processes governing atmospheric escape from planetary bodies throughout the solar system. Advanced computational models attempt to predict the detailed evolution of comet brightness, morphology, and chemical composition during perihelion passage, though the chaotic nature of outgassing processes and structural evolution makes precise forecasting extremely challenging. These models must account for thermal physics, fluid dynamics, structural mechanics, and chemical kinetics operating simultaneously across spatial scales ranging from molecular to planetary dimensions. The irony of perihelion lies in its dual nature as both the moment of maximum scientific accessibility and the beginning of the comet's final dissolution, when millions of years of preservation in the outer solar system give way to rapid destruction under the gentle warmth of distant sunlight. This brief period of enhanced activity provides humanity's only opportunity to study these ancient materials before they disperse irreversibly into the interplanetary medium. International collaborations mobilize their most advanced observational resources during perihelion passage, recognizing that this represents a unique and unrepeatable opportunity to study confirmed interstellar materials under conditions that maximize their scientific accessibility. The coordinated campaign represents one of astronomy's most intensive efforts to characterize a single object, combining data from dozens of ground-based and space-based instruments to create comprehensive records of the comet's physical and chemical evolution. The approach to perihelion transforms 3 Atlas from a distant, barely detectable speck of reflected starlight into a dynamic, evolving system that demonstrates fundamental principles of physics and chemistry operating under extreme conditions, providing natural experiments that extend the boundaries of laboratory science while preserving direct samples of materials that witnessed the birth of planetary systems. Only took the solar system 4.5 billion years to create conditions where thermal energy from a middle-aged star could liberate and illuminate ancient materials for study by conscious observers who developed the tools to decode their cosmic significance. The sublimation process that governs 3I Atlas accelerates exponentially as solar heating intensifies, transforming the ancient nucleus from a stable archive of primordial materials into a rapidly dissipating cloud of vapor and dust that carries with it the chemical record of stellar nurseries that existed before the Sun's formation. This phase transition from solid to gas occurs at the molecular level as thermal energy breaks the weak van der Waals, forces that have held water molecules in crystalline lattices for billions of years, liberating individual molecules that achieve escape velocity and begin their own independent orbits around the Sun while gradually dispersing into the vast emptiness of interplanetary space. The physics of sublimation under vacuum conditions differs dramatically from familiar terrestrial processes, as the absence of atmospheric pressure allows solid ice to transform directly into vapor without passing through a liquid phase. This direct phase transition occurs at temperatures far below the melting point of water ice, enabling significant mass loss from the comet nucleus, even when surface temperatures remain hundreds of degrees below freezing by terrestrial standards. The process demonstrates fundamental thermodynamic principles operating under extreme conditions that cannot be easily reproduced in laboratory environments. Professional researchers monitor the comet's mass loss rate through careful analysis of brightness changes, spectroscopic measurements of gas production, and theoretical modelling of sublimation physics applied to the specific thermal and structural conditions present within the porous nuclear structure. These calculations indicate that 3I Atlas may lose several % of its total mass during its passage through the inner solar system, representing the destruction of materials that have remained essentially unchanged since the epoch of planetary formation. The acceleration of volatile loss creates positive feedback mechanisms, where increased sublimation rates expose fresh ice surfaces to solar heating, leading to further enhanced outgassing activity that can produce rapid, non-linear changes in the comet's appearance and behaviour. This runaway process can lead to complete nucleus disintegration in extreme cases, though most comets survive their perihelion passage with significantly reduced mass and altered surface composition that reflects the preferential loss of the most volatile components. Theoretical models of sublimation kinetics reveal complex relationships between surface temperature, vapor pressure, molecular diffusion rates, and the three-dimensional geometry of gas flow paths through the porous nuclear structure. The sublimation process occurs not only at the visible surface, but also within internal cavities and fractures where solar heating has penetrated sufficiently to raise temperatures above the sublimation threshold for different volatile species. The dust component of the nucleus becomes increasingly prominent as sublimating gases carry away the ice matrix that previously bound refractory particles together, leaving behind concentrations of silicate grains, organic compounds, and metallic particles that can form temporary surface crusts or lag deposits. These refractory residues modify the thermal properties of the surface and can significantly affect subsequent sublimation rates by altering the absorption and conduction of solar energy. Gas dynamics calculations demonstrate that sublimating vapor expands away from the nucleus surface at velocities determined by the local temperature and molecular composition, creating pressure gradients that can reach significant magnitudes despite the overall low-density environment. These pressure effects can contribute to mechanical erosion of the nucleus surface and influence the transport of dust particles embedded within the sublimating ice matrix. The chemical composition of sublimating gases evolves as different volatile species respond to temperature increases according to their individual vapor pressure curves, with the most volatile compounds like carbon monoxide and nitrogen being liberated first, followed by water ice, and finally more refractory materials like organic polymers and mineral components that require higher temperatures for significant outgassing. Laboratory studies of sublimation processes in vacuum environments provide calibration data for interpreting observations of cometary mass loss. Though the complex geometry and heterogeneous composition of actual comet nuclei create conditions that differ significantly from idealized experimental setups, these controlled experiments help establish the fundamental physical relationships that govern sublimation under space conditions, while highlighting the challenges involved in scaling laboratory results to real cometary systems. Advanced spectroscopic observations during periods of rapid sublimation reveal the liberation of trace chemical species that remain undetectable during lower activity phases, including isotopically unusual compounds that preserve information about nuclear processes in stellar interiors and chemical evolution in interstellar molecular clouds. These rare molecules provide unique insights into cosmic chemical evolution that cannot be obtained through study of more processed materials in meteorites or terrestrial samples. The temporal evolution of sublimation rates follows complex patterns related to the nucleus rotation period, orbital geometry, and internal structural heterogeneity, creating diurnal variations, seasonal changes, and long-term secular trends that encode information about the three-dimensional distribution of volatile materials within the original nuclear structure. Professional observers coordinate round-the-clock monitoring to capture these temporal variations with sufficient resolution to constrain theoretical models of internal composition and structure. International research collaborations develop increasingly sophisticated techniques for measuring sublimation rates and their relationship to nuclear composition, employing multiple observational approaches that provide complementary information about different aspects of the volatile loss process. These studies contribute to fundamental understanding of phase transitions under extreme conditions, while providing practical insights relevant to spacecraft thermal control and life support systems designed for operation in the vacuum of space. The sublimation of 3I Atlas represents the final chapter in a cosmic story that spans billions of years, as materials that formed in the cold depths of interstellar space undergo their ultimate transformation back into individual molecules that will eventually disperse throughout the solar system and potentially contribute to the chemical evolution of other planetary bodies. This process demonstrates the cyclical nature of cosmic material processing, where stellar death and birth, planetary formation and destruction, and the endless recycling of chemical elements create the complex web of relationships that connects all matter in the universe. The accelerating dissolution of the ancient nucleus serves as a reminder of the ephemeral nature of even the most stable-seeming cosmic structures, showing how gentle stellar radiation can gradually disassemble objects that survive billions of years in the harsh environment of interstellar space, transforming concentrated archives of primordial information into dispersed clouds of individual atoms and molecules. Only took the universe 13 billion years to create observers capable of understanding and documenting the physics of sublimation processes that return ancient stellar materials to the cosmic recycling system that connects the deaths of old stars to the births of new worlds. The remnants of 3I Atlas disperse along its orbital trajectory with the inexorable persistence of celestial mechanics. Each fragment and dust particle following its own slightly modified path through the gravitational architecture of the solar system, while gradually spreading across millions of kilometers of interplanetary space. This debris field represents the final transformation of concentrated primordial materials back into the diffuse medium from which they originally condensed billions of years ago, creating a temporary meteor stream that may intersect Earth's orbital path at some future date when our planet's motion carries it through the expanding cloud of ancient particles. The largest surviving fragments maintain enough structural integrity to continue modest outgassing activity as they pursue independent elliptical orbits around the Sun, each piece carrying a portion of the original chemical archive while developing its own characteristic pattern of volatile loss and dust production. These mini-comets range in size from small buildings to city blocks, preserving sufficient mass to retain their volatile inventories for years or decades, before thermal processing reduces them to inert rocky cores devoid of sublimable materials. Orbital mechanics calculations reveal that the fragment ensemble will continue expanding along the original trajectory for centuries, with individual pieces gradually separating at velocities measured in meters per second, until they occupy a volume of space comparable to the distance between Earth and Moon. This slow-motion explosion proceeds with mathematical precision, each fragment's motion governed by Newton's laws and Einstein's relativistic corrections applied to the complex gravitational environment created by the Sun and major planets. Professional dynamicists employ numerical integration techniques to predict the long-term evolution of the debris stream, accounting for gravitational perturbations from all major planets, radiation pressure effects on different particle sizes, and the Poynting-Robertson drag that causes small dust grains to spiral slowly inward toward the Sun over timescales measured in millions of years. These calculations require supercomputer resources to track thousands of individual fragments through hundreds of years of orbital evolution. The mystery lies in predicting exactly when and where Earth's orbit might intersect the expanding debris field, creating meteor shower events that would provide opportunities for terrestrial laboratories to analyze confirmed interstellar materials collected directly from the upper atmosphere. Such encounters occur rarely and unpredictably, depending on the precise geometry of orbital intersections and the complex gravitational dynamics that govern the long-term evolution of debris streams in the solar system. Individual fragments experience differential effects from solar radiation pressure based on their size, composition, and surface properties, causing the debris field to develop complex internal structure as smaller particles separate from larger ones and different compositional types follow divergent trajectories. This process gradually sorts the original nucleus materials according to their physical properties, creating distinct populations of fragments with different evolutionary pathways through the inner solar system. The chemical evolution of dispersing fragments proceeds independently for each piece, with smaller objects losing their volatile inventories more rapidly, while larger fragments preserve their sublimable materials for extended periods. This differential processing creates opportunities to study the same primordial materials under different degrees of thermal alteration, providing insights into the relationship between nucleus size and volatile preservation that cannot be obtained through observation of intact comets. Ground-based observers continue monitoring the brightest fragments as they fade from telescopic visibility, documenting their gradual transition from active comets to inert asteroids, as thermal processing removes their remaining volatile components. These observations provide direct evidence for the evolutionary pathway that connects active comets to the population of dormant nuclei that may comprise a significant fraction of near-Earth asteroids. Theoretical studies of debris stream evolution reveal complex relationships between initial fragmentation geometry, orbital dynamics, and the long-term spatial distribution of fragment populations throughout the inner solar system. Computer simulations suggest that materials from individual comet breakup events can remain dynamically associated for millions of years while gradually dispersing across vast regions of interplanetary space. The dispersal process demonstrates fundamental principles of statistical mechanics applied to gravitational systems, where initially concentrated distributions of mass and energy evolve toward maximum entropy configurations through the inexorable operation of deterministic physical laws. The transition from ordered nucleus structure to chaotic debris field exemplifies the second law of thermodynamics, operating on cosmic scales across geological timescales. Advanced space-based telescopes attempt to track individual fragments until they become too faint for detection, creating comprehensive catalogues of debris stream components that will enable future predictions of potential Earth encounters and meteoric events. These observations push the limits of current astronomical capabilities, while providing unique datasets for testing theoretical models of small body dynamics in planetary systems. Professional meteor researchers prepare for the possibility of future shower events associated with 3I Atlas debris, developing specialized detection networks and collection techniques optimized for recovering interstellar materials that might survive atmospheric entry. Such samples would provide the first direct laboratory access to confirmed materials from other stellar systems, representing scientific opportunities that justify extraordinary observational and analytical efforts. The gradual fading of 3I Atlas fragments marks the end of direct observational access to these ancient materials. Yet their continued existence as microscopic particles distributed throughout the solar system ensures that traces of this interstellar visitor will persist for millions of years. Future spacecraft missions or atmospheric collection techniques may eventually recover individual grains that preserve chemical signatures from the comet's brief passage through the inner planetary region. International collaborations coordinate long-term monitoring programs designed to detect and characterize meteor showers that might result from Earth's eventual encounter with 3I Atlas debris. Recognizing that such events could occur decades or centuries in the future when current observational techniques and theoretical understanding may seem primitive compared to the capabilities available to future generations of researchers, the scattering of 3I Atlas remnants across the solar system completes the cosmic cycle that began with stellar nucleosynthesis in ancient supernovae, continued through molecular cloud chemistry and planetary formation processes, and concludes with the return of processed materials to the interplanetary medium, where they may eventually contribute to the formation of new planetary systems around other stars throughout the galaxy. It only took gravity 4.5 billion years to concentrate interstellar materials into a comet nucleus. Then a few months of solar heating to reverse the process and return those same materials to the cosmic medium from which they originated. Darkness returns to the space once illuminated by the ancient wanderer, settling over the orbital path where 3 Atlas completed its singular passage through the Sun's gravitational domain with the same quietude that has characterized the vast emptiness between stars for billions of years. The interplanetary medium closes seamlessly over the dispersed remnants of the comet's passage, individual molecules and dust grains becoming indistinguishable from the background population of particles that drift perpetually through the solar system's extended atmosphere. What remains exists now only in the archived observations, spectroscopic records, and theoretical models that preserve humanity's brief encounter with materials older than the terrestrial planets themselves. The vacuum of space reclaims its dominion over regions that briefly harboured the expanding gases and reflecting dust of an active comet. Temperatures settling back toward the cosmic background radiation temperature that governs thermal equilibrium in the depths between worlds. Solar radiation continues its outward journey at the speed of light, carrying no trace of its recent interaction with the sublimating ice and liberated dust that created temporary atmospheric phenomena millions of kilometers from any substantial gravitational body. Professional observatories turn their instruments toward other targets as 3I Atlas fades below the threshold of detectability, leaving behind only the fading radio emissions and dispersing plasma signatures that mark the final dissolution of structures that preserved information about stellar nucleosynthesis and molecular cloud chemistry from epochs when the Sun itself existed merely as a possibility within a collapsing nebula of gas and dust somewhere in the galaxy's spiral arms. The silence that follows encompasses wavelengths from radio to gamma rays, as the electromagnetic spectrum returns to its background state unmarked by the characteristic emission lines and scattering signatures that briefly identified the presence of ancient water vapor, carbon compounds, and silicate dust in regions of space where such materials normally remain absent for geological ages. This cosmic quiet reflects the restoration of equilibrium conditions that have characterized interplanetary space throughout most of the solar system's evolutionary history. Computational models continue their mathematical evolution in terrestrial supercomputers, processing the final observational datasets while extrapolating the trajectories of dispersed fragments toward future positions that may never be observed directly, but will influence the subtle distribution of materials throughout the inner solar system for millions of years to come. These calculations proceed with mechanical precision, tracking invisible particles through gravitational fields that will guide their motions according to physical laws that operate regardless of whether conscious observers remain present to document their consequences. The return to darkness carries no drama, no acoustic signatures to mark the transition from activity to quiescence in the realm where sound waves cannot propagate, and thermal radiation provides the only evidence of temperature differences between objects and the cold background of empty space. The fading process occurs as gradually as the original brightening, following the same exponential curves that govern radioactive decay and other natural processes where statistical mechanics determines the rates of irreversible change. Archive systems preserve the spectroscopic data, photographic plates, and numerical measurements that document humanity's first detailed study of confirmed interstellar materials, creating permanent records that may outlast the civilization that created them while preserving information about cosmic processes that operated before Earth's oceans formed, or life began its evolutionary journey through geological time toward consciousness and scientific understanding. The restored emptiness extends across distances measured in astronomical units, encompassing volumes of space larger than most stellar systems, yet containing material densities so low that cubic kilometers may hold fewer particles than a single breath of terrestrial air. This rarefied environment represents the natural state of most of the universe's volume, where matter exists primarily as individual atoms and molecules separated by distances that make collisions statistically insignificant across human timescales. Stellar radiation pressure continues its work of sweeping microscopic debris toward the outer boundaries of the solar system, gradually removing the last traces of 3I Atlas from the inner planetary region, where its brief presence provided unique opportunities to study the chemical inventory of environments that existed before the Sun achieved nuclear ignition and began its current phase as a main sequence star. The cleaning process operates continuously yet imperceptibly, requiring millions of years to complete the removal of dust particles from the regions where planets orbit. The darkness encompasses not only the absence of reflected sunlight from comet surfaces, but also the cessation of fluorescent emission from excited gas molecules, the ending of plasma processes that created radio signals, and the termination of thermal radiation from dust grains heated above the ambient temperature of interplanetary space. These various forms of electromagnetic activity fade according to their individual timescales, creating a complex symphony of declining signals across the spectrum. Future archaeologists of astronomy may rediscover traces of 3I Atlas through careful analysis of archived data, extracting new insights from observations that seemed complete at the time of their collection, but reveal additional information when processed using techniques and theoretical frameworks not yet developed. The scientific legacy of this interstellar visitor will persist in digital form long after its physical components have dispersed beyond recovery or recognition. The cosmic recycling process continues its patient work of redistributing materials throughout the galaxy, carrying trace amounts of processed cometary dust toward other stellar systems, where similar objects may be forming from collapsing molecular clouds that contain heavy elements created in the nuclear furnaces of previous stellar generations. This endless circulation connects the chemistry of life to the deaths of massive stars across billions of years of galactic evolution. The space between worlds settles into its accustomed stillness, temperatures equilibrating toward values determined by the cosmic microwave background and the dilute starlight that bathes all regions of the galaxy, waiting with geological patience for the next ancient wanderer to emerge from the darkness between stars and briefly illuminate the processes that created the chemical foundations of planetary systems, biological evolution, and conscious inquiry into the nature of cosmic time. In the returning quiet, only gravitational waves continue their invisible passage through empty space, carrying information about distant cosmic events at the speed of light, while leaving no permanent trace of their passage through regions where matter exists too sparsely to register their subtle effects on the geometry of space-time itself. The story of 3I Atlas draws to its close in the gentle mathematics of orbital mechanics, where trajectories calculated in observatories become memories preserved in digital archives, and ancient ice returns to the cosmic medium from which it first condensed in molecular clouds that no longer exist. The darkness between worlds reasserts its patient dominion over regions of space that briefly glowed with reflected starlight and fluorescent emissions, settling back into the thermal equilibrium that has characterized most of the universe's volume throughout the 13 billion years since the first stars began forging heavy elements in their nuclear cores. What remains exists primarily in the realm of information spectroscopic measurements that decoded chemical messages written in wavelengths of light, photographic plates that captured the visual poetry of sublimating ice and streaming dust, and computational models that will continue processing observational data long after the last fragments have faded beyond the reach of Earth's most sensitive instruments. These scientific records preserve the encounter between human curiosity and materials that travelled through interstellar space, carrying archives of stellar death and molecular birth from epochs when our solar system existed only as a possibility within the gravitational collapse of a distant nebula. The silence that follows encompasses all frequencies of the electromagnetic spectrum, from radio waves that once carried the signatures of excited molecules to gamma rays that never found sufficient material to interact with in the rarefied environment of interplanetary space. This restored quiet reflects the natural state of the cosmos, where vast volumes contain fewer particles than a human breath, yet extend across distances that light requires years to traverse. In this emptiness, gravitational forces continue their invisible work of organizing matter according to mathematical principles that operate with perfect consistency across scales ranging from dust grains to galaxy clusters. The orbital paths of dispersed fragments carry forward through space and time according to Newton's laws, each piece following its calculated trajectory toward future positions that may never be observed but will influence the subtle distribution of materials throughout the solar system for geological ages to come. These invisible motions proceed with mechanical precision, demonstrating how deterministic physical laws govern the evolution of cosmic structures, regardless of whether conscious observers remain present to document their consequences. The universe continues its patient expansion and cooling, carrying the scattered remains of ancient comets toward destinies written in the equations of celestial mechanics and statistical thermodynamics. In the deepest sense, the darkness represents not absence but the fundamental ground state of cosmic existence, the condition from which stars, planets, and eventually conscious beings emerge through processes of gravitational collapse, nuclear fusion, chemical evolution, and biological development that span billions of years. The brief illumination provided by objects like 3i Atlas serves to reveal the underlying structure and composition of this darkness, showing that apparent emptiness contains the chemical inventory necessary for the formation of worlds and the eventual emergence of intelligence capable of studying its own cosmic origins. The return to quietude marks not an ending but a transition, as the materials that once comprised a coherent nucleus begin their next phase of cosmic evolution, as individual molecules and dust grains distributed throughout interplanetary space, available for incorporation into future planetary systems, meteoric events, or other astronomical phenomena that will continue the endless cycle of cosmic material processing. The universe sleeps deeply in its expanding darkness, dreaming of future possibilities encoded in the quantum fluctuations that will eventually grow into tomorrow's stars and worlds.